Hello students, in this video we're going to briefly introduce what confidence intervals are about. So the basic idea is that a confidence interval is a range of values that is used to estimate the value of a population parameter. Each confidence interval has a lower limit and an upper limit. The lower limit and upper limit we obtain for a confidence interval depends on the sample data we collect, the size of the sample, the level of confidence of our interval, and the population parameter we wish to estimate with our interval. So in this chapter, we're going to use confidence intervals to estimate the population proportion P, the population mean mu, and the population standard deviation sigma. The confidence level tells us the success rate of the process we use to obtain the confidence interval is at capturing the true value of the population parameter. So in essence, we are using an interval of values to come up with a likely estimate for the value of an unknown population parameter, right? Whether the parameter is the proportion P, the population mean mu, or the population standard deviation sigma. Some common confidence levels are 80%, 90%, 95%, and 99%. So the confidence level of a confidence interval is usually given as a percentage. All right, and we'll take a look at this with a simulation. So we're going to go ahead and take a look at the following website, which is the Rossman/Chance applet collection. So it's the names of the individuals who developed this website and these applications. And it shows you different simulations for different topics that are discussed in statistics. Now, we won't look at many of these, but what we will focus on in the video is simulating confidence intervals for population parameters. So if you click on that one, another tab will open in your browser. And it allows you to simulate confidence intervals for proportions or for means. So let's go and look at confidence intervals for proportions. And we're going to leave the distribution as binomial. And then the method that's usually discussed in textbooks in statistics classes like this one, for constructing confidence intervals for proportions is called the Wald method, although I don't believe that the book mentions that. Okay, so what we're going to do is we're going to pretend that the population proportion is 0.4. So like, for example, let's say 40% of a population has a certain characteristic or holds a certain belief. Okay, we say that that population proportion is 40%. Now, in reality, we won't know what the population proportion is. Okay, but in the simulation, we can pretend that we know what it is, and let's pretend that it's 40.40 or 40%. Okay, and then we can select the sample size. So I'm going to start small. So I'm going to select a sample size of 10. All right, and let's go ahead and create 100 different intervals. And I'm going to start the confidence level at 90%. All right, so if I change the confidence level, I'm going to recalculate it. Okay, but let's go ahead and sample 100 different confidence intervals for this fictitious population proportion that is 40%, and we're going to see how many of the confidence intervals capture the value of the population parameter, which is 40% or 0.40. And what you'll see here is different confidence intervals. Okay, so the ones that are in green, okay, capture the population proportion, or fictitious population proportion of 0.400. Okay, that's the line here shown in black. Okay, so 0.400 or 0.4. Okay, so the confidence intervals in green, okay, have the value of that population parameter. Okay, and then there are certain intervals, which are in red, okay, that don't capture the value of the population proportion. Okay, like this one here, right, it's too far to the right. Okay, so it doesn't capture the value of 0.40. Okay, likewise this one here, this one here. Okay, but the ones in green, right, do capture that population proportion. Okay, and you can see here the summary of the results, right? So the intervals that contain the population proportion, right, 92 out of 100, Okay, remember our confidence level was 90%, so we would expect about 90 or 90% of our intervals to capture that proportion. Okay, so in this case 92 do. All right, if we sample again, right, we come up with another 100 intervals. Okay, right, and there's like a running total of our confidence intervals that capture the value of the population proportion. Okay, we sample again. So this tells you how many of the most recent 100 intervals, right, contain the value of the population proportion. So 93 do, and then of the running total of the 300 that we've simulated so far, right, 276, right, capture the value of the population proportion. So in other words, what we're doing is we're creating many different confidence intervals, okay, for the same parameter, right? And we're seeing how many of those confidence intervals, okay, contain the value of the population parameter. So in reality, we won't know what the population parameter is. In this case, we're assuming that the population proportion is 0.40. Okay. So we've created 300 different confidence intervals so far. Okay, and we set the confidence level at 90%. Okay, so if you take 90% of 300, okay, you get around 270. Okay, so far, right, 276 of our simulated confidence intervals, right, have captured the true value of the population proportion, which is set at 0.40. Okay, so we're doing a little better than the 90% here. Okay, if we increase the sample size, say from like 10 to 25, right, what effect does that have on our confidence intervals? So let's go ahead and see. Okay, so as you can see, right, as you increase the sample size, it actually increases the width of the interval. We can try again. Let's increase that. So let's say 40. Okay, as you see, right, the confidence intervals get more narrow, which means they get more accurate, more precise. Okay. And again, we did not change the confidence level. So again, we would expect, right, about 90% of these confidence intervals to contain the true value of our population proportion. Okay, so in this case, with a sample size of 40, right, 91 out of the 100, which are shown in green here, right, captured the value of our hypothesized population proportion, which is 0.40. Now, what happens if we increase the confidence level? Let's say from 90% to 95%. Okay, you can see that it actually widens each of the intervals, right? The intervals get wider. Okay, so as you increase the confidence level, right, the interval needs to be wider. Okay, you need a wider range of values to have more confidence. Okay, so in this case, right, 95 out of the 100 intervals capture the value of our hypothesized or fictitious population proportion. And if we increase it to 99%, okay, the intervals get even wider, and we would expect more of the intervals to capture the value of that parameter. Okay, so if we run the simulation several more times where we sample 100 more confidence intervals, we see that out of 400 out of the simulated intervals, right, 394 captured the value of the population proportion. Okay, so based on these results, we can make some observations. Okay, so increasing the sample size will decrease the width of the confidence interval. Okay, and make it more precise. Okay, likewise, increasing the confidence level, okay, makes the interval wider. Okay, and the basic idea behind that is, right, if you have a higher level of confidence, right, so if you create a confidence interval with a higher level of confidence, okay, you increase the likelihood that that interval that you create will capture the true value of the population parameter that you're estimating, right, whether it's the proportion or the mean or the standard deviation. Okay, so a higher level of confidence, right, necessitates a wider interval because it's then more likely to capture that unknown parameter. Okay, so through the simulation, right, we can create any number of confidence intervals that we want. Okay, and see how well it captures the unknown population parameter. But in reality, right, when you do a statistical study, right, you collect your sample data, and then from your sample data you construct your interval. Right, in reality, right, you're only really going to construct one interval. Okay, so based on that one interval, you can say, okay, if I constructed the more intervals, right, from different samples, right, we would expect a certain number, a certain percentage of the confidence intervals to capture the true value of the parameter. And that's the meaning of the level of confidence, right? It tells you how successful the process is at creating a confidence interval that will capture the unknown population parameter in question.